In this lecture, we're looking at motion on an inclined plane. The motion on an inclined plane is a lot like free fall, except that the object falls along a ramp at an angle to the ramp. So this motion basically reduces the free fall acceleration to a component of acceleration along the ramp. Let's consider the ramps shown there, where we look at a ball that is falling or that is sliding down the ramp. We are assuming that there is no friction on the ramp, so the ball slides freely down the ramp, starting from an initial velocity of 0 and then just sliding down the ramp as shown here. So the velocity vector for this object starts off 0 or with no vector, and then it increases as the object picks up speed along the ramp. And you can see that I've drawn the velocity vectors getting longer as it goes down the ramp. So in this frame here, we can look at the acceleration vectors for the object that I drew in the previous frame going down the ramp. The acceleration is a vector, and so since the object is sliding down the ramp with uniformly accelerated motion, it has a constant acceleration down the ramp. So you can see that I've drawn the acceleration vectors to be the same length as the object goes down the ramp. So let's look next in this frame. So in this frame, I've drawn the object again on the ramp. The ramp is at an angle of theta, and so you can see here that the acceleration of gravity points straight down the ramp. And so a component of acceleration along the ramp is A parallel. A parallel is given by g sine theta, and the component down the perpendicular to the ramp is given by A perpendicular and is given by g cosine theta. So based upon this information, we can think of our ramp in the coordinate system where it has x this way, and this would be y. So we can now write our kinematic equations for an object sliding down the incline in 2 dimensions, where we shall have an x component for its motion and a y component. And let's do that in the next frame. So in this frame, I chose a coordinate system as I showed you earlier. So this is the coordinate system shown. Okay, let's make this a little bit bigger so you can see. So I've shown you a coordinate system here. So this is x and that's y. And so along the x-axis, our kinematic equations are just given by the usual kinematic equations. X final equals the x initial, which is our initial position. So our initial position is somewhere here. Final position will be down here. V initial is the initial velocity of the object up here, and delta t is the time it takes to slide down the ramp. And then the next kinematic equation is the final velocity equation. So V final is the velocity somewhere down the ramp. V initial will be the velocity when it is up on the ramp here, and A parallel is the acceleration down the ramp, and delta t is the time it takes to slide down the ramp. This is the same formula, except that in this formula, without knowing the time interval, if you just knew the displacement down the ramp, delta x, you will just put that in here, and then you can calculate your final velocity for the object as it slides down the ramp. Let's look at the next frame. Let's put this back. So in the next frame, so in this frame, I'm just going to rewrite the kinematic equations, but I'm going to replace the A parallel, which is the acceleration down the ramp, with g sine theta. And so with that, I have x final equals x initial plus v initial delta t plus half g sine theta delta t squared. So the A parallel was here, I just replaced it with g sine theta. Final velocity is given the same way. I've just replaced the A parallel, which was in this kinematic equation, with g sine theta. And I've done the same for this kinematic equation. So along the y-axis, you will notice that since there is no motion along the y-axis of the ramp, we don't need to write any kinematic equations for the y-axis of the ramp, since there is no motion along that axis. Let's look at an example in this frame. So in this frame, I've written out an example of a ball that slides down an incline which is at an angle of 30 degrees. I've mentioned that it starts from rest and slides a distance of 20 meters, so I'm giving you delta x to be 20 meters along the incline. Find its final velocity, which is v final, after it has traveled this distance. So here is a solution. This is what you students told me. You said V final was 14 meters per second down the ramp, so we can check it next to see what it is. So since we don't have the time it takes to slide down the ramp, let's look on this frame. Since we don't have the time it takes to slide down the ramp, we know delta x is 20 meters, so we can use our delta x with this in this formula here. We replace the parallel acceleration down the ramp with g sine theta. We already know g is 9.8 meters per second, so we can put that in there. It's negative 9.8, and our displacement down the ramp is negative 20, so we are assuming that it starts at initial position 0 and final, it starts at the initial position at the top, which is 20, and the final position is 0, so the displacement is minus 20. So V final squared is given by this formula here, and so the V final is the square root of 2 times 9.8 times sine 30, which is 0.5, times 20, which is our displacement. So our final velocity here would be 14 meters per second, as you guys told me, so that is correct. We'll take that. And so if you look at it from the point of view of a ramp that is changing, meaning that the angle of the ramp is changing. I initially mentioned that motion down the ramp is a lot like free fall motion, except that it's at a reduced acceleration because it's at an angle, or it's sliding down the ramp at an angle to the actual acceleration of 9.8. So suppose we have a ramp at 30 degrees, it means that acceleration down the ramp is going to be g sine 30, which will be about 4.9 meters per second. If we increase the ramp to 45 degrees, we have an acceleration of g sine 30, so it's going to be 9.8 times 0.7071, and so it goes on and on. So you can see that when the acceleration, when the ramp reaches an angle of 90 degrees, then g sine 90 is 1, and so g is negative 9.8, so the object is now in free fall. Okay. So let's look at this next ramp. So I just mentioned that here, that suppose theta is 90 degrees, we have V final squared equals V initial squared plus 2g sine 90 delta x, which then replaces our g sine 90 with g, since sine 90 is 1. So we just have an object in free fall, since the acceleration a is just equal to the acceleration of gravity. So this is the end of our motion on an inclined plane.